Okay, so today we start a new chapter. Hey, I told your assistant, Özgür, he'll prepare some online quiz or kind of homework. It will have like, you know, 1 day long. I mean, you may take the quiz or you know, homework anytime on that day. There will be 1 or 2 questions, and you will you know, solve it and then submit it. He will grade it. Our aim is not to create another tool to assess you. That's not the you know, main aim. That's extra work for us and for your assistant. Actually, the aim is you know, to make you prepared for the exam. Okay, although you know, ideas in differential geometry are, you know, kind of I mean, they are not difficult, they are not theoretical actually ideas, but you have to be you know, experienced when you are doing calculations. If you make a small mistake during the calculation, then you get nothing. Okay, that's usually what happens. And then, even though you know what's going on, you understand the material, you may not get any credit on the question. Okay, because if you make a small mistake, sign mistake, or if you make a mistake while you are carrying an equation to the, you know, next line, if you make a mistake, then things get so complicated you cannot proceed. And during the exam, it is not easy to find the mistake. Okay, so you have to be well prepared. You know, you have to do a lot of mistakes, but you know, before the exam. So this is a chance for you to make, you know, stupid mistakes. Okay, you may regard it this way. And you, from this quizzes, will be an extra credit. So I will just add it to your total grade at the end of the semester. Okay. Yeah, sure. He will announce you the date, and then you will have 24 hours to take it. So it's like homework, but you know, limited time, and there'll be like 1 or 2 questions. It will be, you know, and homework you have to spend hours. All right, let's start. So this is chapter 2, and the first one is actually something from linear algebra, so-called dot product. So 4 points P, let's say P1, P2, P3, and Q, Q1, Q2, Q3 in R3, the dot product P dot Q of P and Q is defined by the formula P dot Q, which is just P1 Q1 plus P2 Q2 plus P3, Q3. Right? This is probably something you know from even high school. Well, some properties of dot product. Well, it is symmetric, right? In other words, P dot Q is the same as Q dot P. It is clear from the formula, right? It is bilinear. In the sense that, you know, if you have a combination of linear combination of two vectors and you take that product with another one, so A and B are here real numbers, P, Q, R vectors. This is just A times P dot R plus B times Q dot R, right? And it is also by, you know, linear in the second component also. But since we have this symmetry, it is right clear. It is positive definite. This is something important. Positive definite. What we mean is this: P dot P is always positive unless P equals 0. Okay. If P is 0, of course it is 0, but otherwise it is always positive. Okay, so I think everybody saw this. Okay. Maybe I should and maybe it is good to emphasize this. It is 0 only if P equals 0, right? Okay. We have a definition. Norm of a vector is defined as norm of P. We write it this way, and this is nothing but square root of the dot product of the vector P with itself for P in R3. Okay. This is really, you know, if you have right a point P, then this is nothing but the, you know, length of the vector joining this point to the origin, right? It is really the length of the vector. And I have one more definition. If P and Q are points in R3, the Euclidean distance from P to Q is defined to be S dpq, and this is nothing but the norm of the vector p minus q. So you see, we regard sometimes points in R3 as points, sometimes as vectors. Okay, we regard them both ways. Okay. Again, something from linear algebra. Okay, if let's say VP and VQ, no, UP are two vectors in R3 at the tangent space to R3 at the point P, in the tangent space to R3 at the point P, then the dot product of these two, which is defined, above, this is just norm of the vector V, norm of the vector Q times cosine theta, where theta is the angle between VP and UP. Okay, so let me draw the picture here. So I am at the point P and we have two vectors, VP and let's say UP, and this is the angle between them. The dot product is just the length of this vectors multiplied times the angle, cosine of the angle between them. Okay. One more definition. A set of three mutually orthogonal unit vectors to R3 at well, tangent to R3 at P is called, I guess we have seen this definition, but okay, let's see again. It's called a frame at the point P. What's the frame at a point P? A set of three mutually orthogonal vectors. So I have, let's say, yeah, I will tell you, I will describe it in more detail. So let's say something like this, E2 and then E3. Mutual orthogonal means they are all perpendicular to each other, okay, like this. And they all have length 1. So unit vectors. So we have this dot EJ is equal to either 1 or 0, depending on whether I and J are the same or not. So this is Kronecker delta IJ. If So E I dot product EI is 1, but if these are different, EI dot product EJ is 0 if I is different than J. So each vector has length 1, and they are all perpendicular to each other. Tamam mı? Sorusu olan var mı? Anlaşılmayan bir şey olursa yani hemen durdurun. Hatta şunu şuraya yazabilirim belki. We have a proposition. Again, you probably remember from this linear algebra. If E1, E2, E3 is a frame at the point P in R3, and VP is any other tangent vector, then this vector is just, well, these three vectors form a basis for the vector space, the tangent space to R3 at the point P. Therefore, any other vector can be written usually as a linear combination of these three vectors. The nice thing about being a frame is that the coefficients of the linear combination will be determined by the inner product. Namely, we have just VP dot product E1. This is the real number times E1. VP dot product E2 times the vector E2, and VP dot product E3 times the vector E3, right? I guess you all remember all these, right, from linear algebra. That's, of course, not true for a general, basis. If you choose an arbitrary basis, you can write V as a linear combination of those basis vectors, but computing these coefficients is not that trivial, right? You have to solve a system of equations. All right. Any questions? One last thing. No, not one last thing. I have still a page. Okay, now if E1, so let's consider a frame, and the components of that frame vectors are as follows. A11, A12, A13. E2 is the vector given as E21, E22, E23, and E3 is the vector A31, A32, A33. So if this is a frame, at a point P, then the matrix is called which matrix? Matrix A, which has those numbers as coefficients. Okay, this matrix is called the attitude matrix of the frame E1, E2, E3. Okay. All right. For tangent vectors, VP, which is V1, V2, V3, and indeed I have to write P here, but you know, we just drop it from the notation for simplicity. U1, U2, U3. If I have two vectors, their cross product is defined to be the vector. Let me write it on this board. Bu arada okay. Bu ikinci tahtaydı. Okay. All right. Okay. So the cross product, which is denoted as VP cross UP, and it is nothing but this expression. So okay. Let me write it this way. IJK V1 ya da şöyle diyeyim. Elimdeki notta yanlış yazmışım da o yüzden şöyle diyeyim. Bu cross product, suppose that the cross product is denoted by WP and the first component of W, second component of W. Böyle olur mu? V1, V2, V3. Yani notasyon olarak bu olur mu diye düşündüm ama bu da iyi bir notasyon değil. Şöyle diyeyim. But then they are not real numbers, right? They are vectors. Okay, let me stick to the old notation. So what is this? The first component is just V2 U3 minus V3 U2, and then okay, U1 3 minus U3 V1, and the last one is V1 U2 minus V2 U1. Okay, so the components of the cross product are determined by the determinants of the minors of this 3 by 3 matrix. Note that U cross V is minus V cross U, because if you interchange these two vectors, you interchange the rows of this matrix. Therefore, the determinants will pick up a minus sign. And we have a lemma. Or vectors. Tangent vectors. The norm of the cross product is just norm U squared times sorry. Okay, and actually this thing is also equal to the following. So it is equal to this one and also equal to the following. Remember, U dot V just theta, right? Theta being the angle between these two vectors. So I have U squared V squared, U squared V squared, right? So we have U norm U squared, norm V squared, and then I have 1 minus cosine squared theta is just sine squared theta. The proof of this is easy, just direct computation. Okay, you can just do this using, the definition, direct computation. Okay. Sorusu olan var mı? Peki, the second section, so section 2.2. Now we start the study of curves. All right, so now let alpha be a curve. Here, of course, where this is an interval in R. With alpha t is a curve in R3, so it has 3 components, and the component functions are denoted by alpha 1, alpha 2, alpha 3 for some functions. Alpha I from I into R. Okay. Then the velocity vector of T at t, at the point t, is defined to be the vector alpha prime t. This is just, you just compute the coefficient, derivative of coefficients at the point t. This is a vector tangent at the point alpha t. Suppose this is the curve in the space, something like this, okay? And this is the point alpha t, and your velocity vector is something like this, alpha prime t. Okay. Oh. All right. Okay. Now, kamera, evet. Teşekkürler. Okay. The speed of the curve at t is defined to be norm of the velocity vector. So it is this gadget. Okay. Velocity is a vector, right? Speed is the length of that, right? Speed is what you read in this, speedometer when you are driving your car. But velocity is, something else, right? It's a vector. All right. What else? If you integrate, of course, speed, obtain the distance traveled, right? Or the arc length. In this case, the arc length of alpha t from t equals a to t equals b is defined to be the integral a to b alpha prime t dt, right? Integral of the speed is the well, path traveled, right? Length of the path traveled, or the arc length. So Suppose we have something like this: alpha A, alpha B, and you have the velocity vector alpha prime t. You take the norm of this vector and you integrate from this point till this point, from t equals a to b, and you obtain the arc length, right? The length of this path. Okay, now a curve alpha t is called unit length if not unit length, unit speed if alpha prime t is equal to 1 for all t. So if you travel the path with unit speed, then it's called a unit speed curve, okay? We will consider unit speed curves to define geometric properties of a given curve. If you don't take unit speed, then things get complicated. Well, you will see, in the coming up lectures. But the idea is the following: if you accelerate, on a straight line, you feel, a force, right? And it is not. It may not be easy to identify whether you get that force while you are driving on a straight line, but since your speed is accelerating, or maybe you are just experiencing some other force. Maybe you are turning, okay? You may feel a force like that. So to eliminate that kind of confusions, we only work with unit speed curves. Of course, not all curves are unit speed, but you can always find a unit speed curve, right? A curve, you may consider the image of a curve as a road, and a unit speed curve is a travel with unit speed, okay? Peki, zamanım var mı? Varmış, tamam. Okay, if it is unit speed, if alpha t is a unit speed curve, we say that alpha t is arc length parameterized. Right? Why arc length parameterized? Well, it is because of the following. Suppose this is your curve, and it's a unit speed curve. Suppose you are at this point at time, let's say 2, okay? If you are at this point at time 5, if it's a unit speed curve, then you know that the arc length here is just 5 minus 2, 3 units, right? That's why it's called arc length parameterized. It is parameterized by the arc length. Okay. If you move from a point and if you measure how much you travel, then that point is just alpha of this point plus amount you travel, the distance you travel. Okay. That's why, you know, a unit speed curve is called arc length parameterized. Alpha t, alpha prime t, and alpha prime t is always 1, rho t. Okay. Regular curve'ü tarif ettim mi ben? Etmedim. Okay. Şöyle söyleyeyim definition. Bir ara söylemiş olmam lazım ama söylediğimi hatırlamıyorum. O yüzden şimdi yapayım. A curve alpha t is called regular if the velocity vector is never 0. Okay, if alpha prime t is never 0 for all t. So regular means your velocity is never 0. Okay, is never 0. Right. At each point, your velocity vector is non-zero. Remark, a curve like this with this image cannot be regular, right? Let's say a curve like this cannot be regular because you cannot just move on this curve without stopping, right? When you come to this point, you have to stop and go backwards. So such a curve cannot be regular. But it can be parameterized, you know, with smooth functions. It may not be exactly this gadget, but if you consider this curve, alpha t equals t squared, t cubed, x and y coordinates, its graph is something like this. And these functions are, you know, nice functions. They are differentiable and so on. But you see at this point, the derivative at 0 is equal to 2t and 3t squared. When you plug t equals 0, you get 0, 0. So it kind of corresponds to this. The shape of this, it's not this one, but something similar. Actually, you know, if you just let this x and this to be y, then the equation is just y squared is equal to x cubed. Y squared x cubed. Y'ye göre simetrik olacak. Y yerine eksi y yazabilirsiniz. Evet, o zaman gerçekten de buymuş. Şöyle. Şunu gibi. Ve x her zaman pozitif, right? X is always positive because we have y squared here and it is symmetric with respect to x-axis. If you replace y with minus y, you are still on the curve. So it is really this curve. Yes. Unit speed demek yani hızınız hep 1. Dolayısıyla siz bir noktada buradaysanız, diyelim ki zaman 2 olduğunda buradasınız. 3 birim zaman sonra, mesela saatte 1 kilometre gidiyorsunuz, 3 saat sonra alfa 5'te olacaksınız. Yani sizin parametreniz, buradaki parametreniz aslında sizin arc length'iniz. Yani şöyle diyeyim, if this is, let's say, the point, your starting point, okay, alpha 0, then, and this point is alpha t, the arc length here from 0 to t is just t, okay? Yani gittiğiniz yol bunun içindeki parametreniz. O yüzden arc length ile parametrize edilmiş eğri diyoruz. Tamam mı? Probably, but I'm not 100% sure. Yeah, but I guess your question is more like, can we find a parametrization for a curve which is regular, right? If it doesn't have a singularity, probably yes. Yeah, okay. Yani arkadaşınızın sorusu şu, diyor ki şu eğri için şu parametrization hani regular değil. Sıfırda durmak zorundasınız. Ama hani benim yazdığım bu parametrization olmadı ama belki başka parametrization bulabilir misiniz, right? So this parametrization certainly doesn't make this point, you know, the velocity vector at this point is certainly 0. But the question is, can we find another parametrization so that the velocity vector is not 0 here? But, you know, if you think of just physically, you cannot, right, for this curve. Unless you make a jump at this point. If you jump in 3 space and come back, then you can do it. The idea is this. You put an extra coordinate here, okay? So t squared, t cubed, and then put another coordinate. So if you travel also in 3 space, then when you take the derivative of this, you will get 1 here. It is not 0, so it becomes regular. But the projection of this path to the xy plane is still this. Yani x-y düzleminde bakarsanız hala bu eğri üzerinde gidiyorsunuz ama havada bir paranda atıyorsunuz. O zaman regular oluyor. Yeah. Yani motosikletle gidiyorsanız durmadan bu yönde gitmek için havada atmanız lazım. Çok tavsiye edilen bir şey değil ama Okay. This is a name. This procedure has a name in algebraic geometry called blow up. You blow up the plane. You call it blowing up the plane. But that's another story. Maybe not. It's something like that. Okay. Okay, I have only 1 minute. Let me stop at this point.